Okay, so in this section we're going to talk about trigonometric substitutions, which should not be confused with the trigonometric integrals we were doing in the last section. So generally you're going to use trigonometric substitutions when you have some constant squared plus x squared, or it could be u squared, or you have a constant squared minus x squared, or a constant squared minus u squared, or you might have x squared or u squared minus some constant squared. So generally, let's just say that you're dealing with u, which is the sum function of x. If the integral can be in the form a squared minus u squared, then you generally would use the substitution u equals a sine theta. And the reason is because when you use an identity, then you would find out that a squared minus u squared will actually equal a squared cosine squared theta. And then if you have a squared plus u squared, you'll let u equal a tangent theta, because when you simplify a squared plus u squared with that substitution, then you'll end up with a squared secant squared theta using this identity. And then if you have u squared minus a squared, you generally want to let u equal a secant theta, so that you'll end up with u squared minus a squared would equal a squared tangent squared theta using the substitution identity here to get that. Now, so what I've got here is this first example here. I've actually got, I'm going to show you an example of the a squared minus u squared case, the first one. So here, think of u as x here for just a minute. So this would be like 1 squared minus u squared. Now I don't really need to bring the u into play here, so I'm just going to say that x is the u. So in this case, I would let the u, in this case the x, equal a sine theta, like it says here. So let x equal a sine theta. Now since a is 1, because the square root of 1 is 1, so I have 1 sine theta. So x is 1 sine theta. Now, if you plug that into here, this 1 minus x squared down here, you'll see that you get 1 minus sine squared theta, and 1 minus sine squared theta is cosine squared theta. So it's consistent with what I said up here, that if the a squared minus u squared will be a squared cosine squared theta, and since a is 1, 1 squared cosine squared theta is just cosine squared theta. Now also you need to get the dx, so since x is sine theta, then dx would be cosine theta d theta. Now we just go back and start plugging things in. So we have x cubed here, so since we know x is sine theta, that would just be sine cubed theta. And in here we have 1 minus x squared, but we know that's cosine squared theta, so square root of cosine squared theta there. And we have the dx, and we know the dx from up there is cosine theta d theta. Well, so you have sine cubed theta, and the square root of cosine squared theta is the absolute value of cosine theta, but we'll just assume it's positive. So cosine theta would cancel with cosine theta, and I just get sine cubed theta d theta. So now I can integrate this using my tricks that I learned in the previous section. So write this as sine theta times sine squared theta, and then replace sine squared theta with 1 minus cosine squared theta. And then let's distribute the sine theta. So sine theta times 1 is sine theta. Sine theta times cosine squared theta is sine theta times cosine squared theta. I left off the d theta there. But so anyway, so if you integrate the sine theta d theta, that's easy. That's just going to be minus cosine theta. And let me just tell you, just to avoid spending so much time on this, to integrate this, why don't you let u equal cosine theta, then of course your du would be minus sine theta d theta, and then you can use that substitution to integrate u squared, and so you would get u cubed over 3. So you would get u cubed over 3 where u was cosine theta, so that would give you cosine cubed theta over 3. So that's how I got that. And anyway, if you just go ahead and do the substitution on that, letting u equal cosine theta, you'll see that and actually du would be minus sine theta d theta. That's why the sign changes to positive. Okay, then the last thing I need to do is figure out a way to get back to my original variable x. So what we're going to do here is realize that from up here, since we know that cosine squared theta is 1 minus x squared, then cosine theta must be the square root of that. And remember, that's to the square root of that is 1 minus x squared to the 1/2 power. So let me write that for you. So cosine theta is actually equal to 1 minus x squared to the 1/2 power. So now if we go back to this, we have 1/3 cosine cubed theta. Well, all you would have to do is cube this, since that's cosine theta, so cube that, and you get 1 minus x squared to the 3/2 power. And then for the minus cosine theta, just replace the cosine theta with this 1 minus x squared to the 1/2 power, or the square root of 1 minus x squared, and then add your constant. And there's your final result there. Now the next one, notice on this next one I have just dx over 4x squared plus 9 quantity squared. So in this case, my u is 2x and my a is 3, because I have 2x quantity squared gives me 4x squared, and 3 squared gives me 9. So I can think of this as a squared plus u squared. I know it's written backwards, but it's really the same thing. U squared plus a squared is the same as a squared plus u squared. So this is u squared plus a squared. And so in that case, what you want to do there is you want to let u, which is my 2x, let that equal a, which is 3 times tangent theta. So in that case, 2x would equal 3 tangent theta. Now let's go ahead and solve for x, so we'll know what x is. X would be, if I divide both sides by 2, would be 3/2 tangent theta. And then that would mean that dx is 3/2 times secant squared theta, d theta, just the derivative. And then I'll let you do this, but if you figure out what is 4x squared plus 9, well, that's just 2x quantity squared, so that would be 3 tan theta quantity squared, so that's 9 tangent squared theta, and then plus 9, and then you can factor the 9 out, and you get tangent squared theta plus 1, and you can see that's where we got the 9 secant squared theta. So if you look at the beginning of the notes, I told you you would end up with, that's what you would end up with there. Okay, so those are the calculations we need to make before we can solve the integral. Okay, so now we're going to replace the dx with the 3/2 secant squared theta d theta from up here. We're going to replace the 4x squared plus 9 with the 9 secant squared theta that we had up there. And then of course we're going to square that. So when we square that, we get 81 secant to the 4th theta. And I factored the 3/2 out of the integral, and I have secant squared theta in the numerator. And then you can divide that into this and get secant squared theta in the denominator. And let's see, I went ahead and pulled 1 over 81 out, multiplied it by 3/2, and got 1 over 54. So now that's 1 over 54 times the integral 1 over secant squared theta d theta. And that's 1/54 times the cosine squared theta d theta. Then what I'm going to do next is I'm going to use an identity for cosine squared theta. So I can replace cosine squared theta with 1/2 1 plus cosine 2 theta. So I'll pull the 1/2 outside of the integral, and I'll leave the 1 plus cosine 2 theta in here. And then 1/54 times 1/2 is 1 over 108. And then when I integrate this, I get theta. And when I integrate this term, I actually get sine 2 theta over 2. And since sine 2 theta over 2 can be written as 2 times sine of theta cosine theta, then the 2's would cancel. So what I would finally get would just be sine theta cosine theta there. So putting it all together, I'm going to get 1 over 108 times theta plus sine theta cosine theta plus a constant. Now I still need to figure out I need to replace theta, and I need to replace sine theta and cosine theta with functions of x. Well, 2/3 x equals tangent theta. I can get that up here from here. So I can solve this for tangent theta and get that 2/3 x equals tangent theta. Then I can solve for theta. So theta would be the arctan of 2/3 x. So I just replace that with the arctan of 2/3 x. And then sine theta, you'd have to get your triangles to do this, but I'm sure you know how to do it. So since we know that tangent theta equals 2x over 3, you could do your little triangles and figure out that sine of theta is 2 over the square root of 4x squared plus 9, and that cosine of theta is 3 over the square root of 4x squared plus 9. So then sine theta times cosine theta would just be the product of these two expressions, and that would just give you 6x over 4x squared plus 9. And then you have plus a constant, of course. Okay, so that's the second case. Okay, here's the third case. You have x squared minus 25, so that's like u squared minus a squared. So let's let x equal 5 secant theta, then dx would be 5 secant theta tangent theta d theta, and then of course x squared minus 25 would actually be 25 tangent squared theta. You can do that if you want to put the 5 secant theta in here and then work it out, but you'll see that this will equal 25 tangent squared theta. So replace x squared minus 25 with 25 tangent squared theta, replace x with 5 secant theta, replace dx with 5 secant theta tangent theta, and then simplify. So you'll get 5 tangent theta over 5 secant theta times 5 secant theta tangent theta, and the secant thetas cancel, these 5's cancel, so you end up with a 5 times tangent squared theta, and then you replace tangent squared theta with secant squared theta minus 1, and then you integrate that, and so you get tangent theta for secant squared theta, and you get theta for the minus 1, and then of course you multiply that by 5. So you get 5 tangent theta minus 5 theta plus c, and then if you go up here and solve for theta, you'll see that theta is the arcsecant of x over 5, and you can show that tangent of theta is equal to this square root of x squared minus 25. So then you can replace theta here with that arcsecant, and you can replace tangent theta with this radical, and so your final answer would be 5 times this square root minus 5 times this arcsecant plus a constant. There's two practice problems here, so you can freeze the video and write them down and work on them if you want. The answers are given. On the next video, if you want to look at it, I'm going to go ahead and do a short video of finding the area of an ellipse using the trigonometric substitution. And so it's a little bit too long to squeeze onto this video, so I'll put it on a next video. And so we'll find a formula for finding the area of an ellipse. Now you know how to find the formula for you know the formula for an area of a circle, but what about the formula for the area of an ellipse? Okay, so when you see the next video, you'll see how to figure that out.